Okay, this is going to be the video for AP Statistics, Chapter 26, which is on Chi-Squared tests, and this will finish the notes. We had a first video that covered two of the three tests, and we're going to add on the third test and talk about how you pick which test to run. Just to review where we were in the last video, we said that we have something called a Chi-Squared goodness of fit test. That's if you're comparing, say, one set of samples, like the colors in a bag of M&Ms, to a set of expected values because you were given percentages to that you expect to happen. So if you're comparing one sample of counts for a set of categories to a set of given percentages, that's a goodness of fit test. How do these counts fit those given percentages? But if you don't have given percentages, like a historic value to compare to, you can also compare across categories. You can compare a bunch of categories across different populations like this. Like in 3 different years, you can look at the distribution in different categories of different kinds of electrical engineering, different kinds of engineering degrees, electrical, mechanical, chemical, civil, something like that. And so in that case, what happens is the percentages that's expected comes from the data itself. And you're comparing, it's like a 2 proportion test, except you're comparing multiple proportions across multiple populations. And it doesn't have to be just restricted to 2. You can have 3 or more. Okay, the last test that we can do is very much like the test for homogeneity. They're almost identical. This one's called the Chi-Squared Test for Independence. This one also uses a table. It also has 2-dimensional situation here. We have counts of 2 things, right? But there's a subtle difference here. What if the columns, like maybe we have gender here, we're going to just go with 2 genders, male and female. And then we had, remember we had this test, this question way earlier on, actually in Unit 1, way back when at the beginning of the year. A researcher asked children which of 4 different emotions they associated with the color red. The results were recorded by gender, male and female. Is there an association between gender and emotion attached to red? In other words, are the variables gender and emotion for red considered independent of each other? And we did this way before. We said, well, we can have these counts of how many kids pick joy, happiness, love, or anger in the males and the females as being what red means. And so far, what we had to do was we did these side-by-side segmented bar graphs, right? We said we could figure out what the total number of people were in the male and the female category, take the percentages and write these as percentages. And then we said if these percentages were pretty close to each other, and our kind of rule of thumb was if all of these were less than 15% different, then we would say they're close enough to say that this distribution is independent of gender, right? That was and remember we said later in the course, we will have a way to answer this question concretely. Are those differences statistically significant? And now we finally can. Okay, so we're comparing a percentage, a distribution say, joy, happiness, love, and anger, right? But we're comparing it across 2 populations, a male and a female, right? It's very much like this test here that we did before, where we were talking about the different percentages of degrees across the different years here. But there's a subtle difference. In the homogeneity case, we literally had 3 different populations, right? Like this was a set of students who graduated in this year, and this was a completely different set of students here, and a completely different set of students. So it really represents like 3 separate samples. And in each sample, we said what percentage are electrical, mechanical, civil, and so on, right? So it's like 3 separate populations, 3 samples, looking at the distribution of a variable across multiple populations. This thing here with the kids is a little different. It's not really 2 different sets of samples or 4 different sets of sample. This is really one big class, right? It's one sample. But in this class, we ask each kid 2 questions, right? Which word do you associate with the red, and what is your gender, right? And so we really have 2 variables for each element in a single sample. And so what we're trying to find is, are the 2 variables for that single sample independent of each other? That's why this one is called a Chi-Squared Test for Independence. But this one's called a chi-squared test for homogeneity because we're trying to show whether or not the percentages of this variable are homogeneous across all the populations. Here, we're trying to show whether or not the variables depend on each other in some way. Okay, so what's different about a chi-squared test for independence is that we write the hypotheses differently, right? We would say for the null hypothesis, the variable gender and emotion for red are independent, meaning that these differences are not significant. And then the alternate one that would be noteworthy would be gender and emotion for red are not independent, or emotion for red depends on gender, or some wording like that, where the differences are significant. But the way we actually conduct the test is exactly the same as we would do for homogeneity. We would still take our calculator here. We would still go to the matrix here. We would take matrix A and edit it and make it, in this case, 2 rows by 4 columns. So 2 rows by 4 columns. And we would be entering the observed counts. 28, 20, 40, 18, 61, 25, 80, and 60. And then we would still run the exact same test. We would run the chi-squared test on matrix A. Let it put expected counts in matrix B. And you would get a chi-squared statistic and a p-value. In this case, this p-value 0.103 would not be below 0.05. So we would say we fail to reject the null hypothesis. Therefore, we do not have sufficient evidence that emotion for red depends on gender. In other words, this is the real way to show whether these percentages are big enough. And in fact, look at these percentages. They're all not exactly the same, but the biggest difference here is 10. And remember, we said the rule of thumb's around 15. So it's not surprising to me that this official chi-squared test now shows that there doesn't seem to be any connection, right? These are still independent. Okay. Now, when we're actually writing up an analysis here, and we'll do that here in a second with an example, we should check conditions. So I am going to show you how to do a problem from the required practice packet. Let me pick a good one here in a second that we'll look at. I'll probably work the practice quiz problem. But before we do that, let me just point out a couple of things about this. So both the independence test and the homogeneity test are two-way table analysis. It just really depends on how the data were collected. Let me give you another example that's really, hopefully, will bring this point home. If you said, ask a simple random sample of voters 2 questions, and each voter answers with both these questions. Do you support building a border fence, and what's your party affiliation? And so we track Democrats, Republicans, and the people who support the border fence and oppose the border fence, okay? Because this is a sample, and we asked 2 things for each element in the sample, this is a chi-squared test of independence, okay? On the other hand, if we did the data this way, divide a set of voters into 2 groups or into 3 groups based on party affiliation. So you took voters, a pool of voters, and you divided them into Democrats, Republicans, and other parties. And then within each of those populations, or each of those each of those populations, you took an SRS of each group. So you took a random sample of Democrats, a random sample of Republicans, and a random sample of other parties, and you asked them one question: do you support a border fence or not? And kept track of the counts. That would be a chi-squared test of homogeneity, because this is about whether or not the percentage variation here is homogeneous across the 3 populations. This is about whether the party variable is dependent or not dependent on support for the border fence, right? So it really has to do with how the data was collected, whether or not it was from a single sample or multiple samples from multiple populations. Okay, so we've already summarized it kind of. Goodness of fit test is when you have one population and you're examining one variable with multiple categories. This is the form of the hypotheses. All proportions match for the null, at least one proportion doesn't match for the alternate. If you have multiple proportions, you're examining one categorical variable across all of those, then you're going to say the null hypothesis is the proportions are homogeneous across the distributions, and the alternate is at least one set are not homogeneous. And then if you have one population, again, from one sample, but you're examining 2 different categorical variables, then the null hypothesis would be that those variables are independent, and the alternate would be that they're not independent. That would be a chi-squared test for independence. Okay, just to see this, let me go ahead and open up a, if I can find it, the practice packet, and let's just do one so you can see what it looks like to write up an analysis. So if I go to stats, chapter 26, required practice. Do I have that? Let me look. Let me actually open up the practice quiz. And we'll do that. Okay, so let me go to the practice quiz page of the required packet. And let's do this first one. Let me just talk about what they are, and then we'll just do them real quick. Can I write on this? Let's see, I don't know if I can write on this. No, I don't think I can. Okay, let me grab the screens here, because I really think it would be advantageous to just show these, just do all three of these as part of this analysis. So here's this first question. We'll just do this right here. Okay, a biology professor reports that historically grades in her introductory biology course have been distributed as follows. She usually gives 15% A's, 30% B's, 40% C's, 10% D's, 5% F's. Grades in her most recent course were distributed this way. She had a large college section or something, and she gave out this many of each grade. We're going to do a hypothesis test to see whether or not this professor's grade distribution has changed, right? All right, so the first thing we would do is, what kind of test do we have? Well, we have historic values here, right? So that's going to make this a goodness of fit test. We're going to do a chi-squared goodness of fit test. We'll go ahead and write that, identify what the test is. And that means that the null hypothesis is going to be that the grade distribution matches historical values or historical percentages. The alternate is that grade distribution does not match the historical percentages. Okay, we have to check conditions. Let me change colors here. So the first condition is that we have count data, right? We have to have an SRS, or representative data, and that the expected counts are at least 5. Okay, do we have count data here? Definitely. This data is counts. That's met. Do we have a simple random sample? Well, no, but this year is representative, right? The whole point of this is to tell whether the current year represents the past. So if we're including her grades here, definitely that's representative of how she grades. And then the expected counts. Now, to do this, we're going to have to actually compute the expected counts. So we'll have to do a little bit of work here. The first thing we're going to do is add up all these numbers here and find out how many people were in her class. So with a calculator, I could say, all right, let's just add those numbers up. We have 89 plus 121 plus 78 plus 25 plus 12. So that turns out to be 325 students. And then I'm just going to take percentages and say, what were the percentages? Well, if we were going to have 15% have A's, then the expected count would be 15% of the 325 is how many A's we should have. So I'm just going to take 325 and multiply by 0.15 to get 15%. And that number turns out to be 48.75. Okay, same thing here. I'm going to have this time 30% B's. So if I take 30%, 0.3 times 325, that should be 97.2. So below the slash here, I'll put 97.5. And if you do that for 40% for C's, 10% for D's, and 5% for F's, you end up getting 78 is 130 expected. 40% of 10 for the D's, we should have had 32.5 D's, and we should have had 16.25s. Those do not need to be integers. They're supposed to be typically non-integers, I believe. I'm going to see when we enter them. I believe the calculator will allow me to enter those as that. Let's see what happens. If for some reason the calculator chokes on that, then we'll round this to the nearest integer. But I believe expected counts are supposed to normally be non-integers. All right, so now we're going to use lists, right? The chi-squared test to determine the p-value is we're going to perform a chi-squared test, chi-squared goodness of fit test in a calculator. Okay, and there's really only one thing we have to specify: degrees of freedom. Since we have 1, 2, 3, 4, 5 categories, we're going to have a degrees of freedom of 4 because it's number of categories minus 1. So if I go to the lists, let me go ahead and clear those lists first by going memory, clear lists. And then in list 1, we're going to put the observed counts, 89, 121, 78, 25, and 12. And then right across from that, we'll put the 48.75, 97.5, 130, 32.5, and 16.25 for the observed counts, or for the expected counts. Okay, at this point, we can, now that we have the expected counts, we can finish the conditions because we have to check that the expected counts are at least 5. All of those values are at least 5. So now I can use this as the reason why I can say, yes, this is true. Now that I have observed counts in list 1 and expected counts in list 2, I can go to stat and run the chi-squared goodness of fit test. List 1, list 2, we're going to set the degrees of freedom to 4 because there's 5 categories, and calculate. All right, and so this gives me what comes out is chi-squared statistic is 62.5. The p-value is 8.5 times 10 to the negative 13, which is approximately 0. And the degrees of freedom were 4. We already recorded that. Okay. We may need that contribution thing in the next part. So I'm going to just go ahead and write up the answer now. So we would say with a significance level of 0.05, p-value of approximately 0 is low. So we reject the null hypothesis. And therefore, since we are rejecting, we do have sufficient statistical evidence to conclude that this professor's current grade distribution has changed from historical values. Now, we can't say for sure what's going on yet as far as why, like what's low, what's high, just from looking at the counts. You have to look at the chi-squared contributions. So in part B of the on the bottom of this page, there's a second question. So let me go ahead and we'll answer that as well. Which grade impacted the decision the most? Explain the meaning and the context of the question. So the second part now, we could say, all right, so it didn't match. What's the issue here? Well, each of these categories has a chi-squared contribution, and whichever chi-squared contribution is highest is going to be the one that's going to be the most responsible for this difference. So what we should say here is we should list out the chi-squared contributions. So the chi-squared contributions from this array are, for A's, it's 33.2. I'm looking at this array here, and I haven't hit any buttons yet, so I can move to the right and see that the second category is 5.6. That was B's. And then the C's and the D's and the F's, if I keep scrolling, the next category is the chi-squared contribution for C's. That was 20.8. 20.8. And then D's are 1.73. And then the F's are 1.11. So it looks like the biggest change came from the A's and the C's, right? They had the biggest chi-squared contribution, so they were the furthest away from what we were expecting. And if we look, we were expecting to give 48 A's, but we gave 89 A's. So it looks like this professor is giving more A's and fewer C's. So there's more A's and there's fewer C's. Okay, so in context, maybe I would say the largest chi-squared contributions are from A's and C's. So I'm doing this in context. This professor now gives more A's and fewer C's than before. So that's how you use the chi-squared contribution in context. All right. Let's look at the second page of the practice quiz for the Chapter 26 required practice packet. Let's take a look at this problem here. So this problem says, as part of a survey, students in a large statistics class were asked whether or not they ate breakfast this morning. The data appears in the following table. Okay. And it looks to me like it says students in a large statistics class. That is a single sample. Since that's a single sample, that means we're keeping track of two variables, gender or sex and breakfast, in a single sample. That makes this a chi-squared test of independence. Okay, so we're going to run a chi-squared test of independence. Is there evidence that eating breakfast is independent of the student's sex? And they actually gave us a nice clue in the problem. This is supposed to be chi-squared test of independence if they're asking me whether or not these things are independent of each other. Okay, in that case, then we would run a right hypotheses this way. The null hypothesis would be eating breakfast is independent of gender. So gender has no connection with whether or not people eat breakfast or not. And HA would be eating breakfast depends on gender in some way. Like one of the genders is more likely to eat breakfast than the other. Okay. We have to check conditions. So the conditions are that we have counts, which we do. We have counts here. This is the data right here. We have an SRS. As part of a survey, students in a large students work. I mean, it didn't really say. We don't have an SRS here, but we can assume these students are typical of all students. So we could generalize this result, at least maybe to the students in this university. And then the last one is expected counts are at least 5. Now, we have to wait till we run the test to look at matrix B to see if that's true. So we're going to wait and fill that in later. Okay, the next thing we're going to do is we're going to say we're going to run a chi-squared test of independence in a calculator. And that requires that we enter the data in a matrix. So let's go back here to matrix A. I'm going to edit it. The data itself is just this part in the middle here. So I've got 2 by 2. So I can say 2 by 2 and enter the counts, 66, 66, 125, 74. And then I can quit out of that, go to stat, and then over here to tests and scroll up from the bottom until I find the chi-squared test, not the goodness of fit test, the regular chi-squared test. Run it. It's observed in A. They'll put the expected counts in B for me, do the calculate. We're going to write what comes out. We got a chi-squared statistic of 5.339. P-value was 0.0209 with 1 degree of freedom because it's rows minus 1, which is 1 times columns minus 1, which is 1. 1 times 1 is 1. And that means my p-value is 0.02. So I would have to finish with the conclusion paragraph with alpha 0.05, p-value equal 0.0209 is low. So we reject the null hypothesis. Okay, so we reject the null hypothesis and say we do have sufficient statistical evidence to conclude eating breakfast depends on gender. Okay, because yeah, just that the difference shows there's a difference here, right? If I were to now maybe take a closer look at this data, I could say, all right, maybe I could find the conditional distribution of eating breakfast over gender. So what percentage of the males ate breakfast? That would be 66. You wouldn't have to do this part to answer the question. I'm just curious. 66 out of 132 means that this was 50% of the males ate breakfast. 125 out of 199. So out of the 199 females, 62.8% ate breakfast. So about 63% ate breakfast. So what we're saying here is that, yeah, in this sample, in this particular classroom, more females, 63% ate breakfast than the 50% of males ate breakfast. But what this is saying is that if you were to take this and extend it to a larger population of maybe all the students in the university, it is true, statistically significant difference that females eat breakfast more often than males. Okay. So that would be that question. Let's look at the third question, last question on the practice quiz, just to kind of tie it all together. All right, so it's on another page. Manufacturing plant for recreational vehicles receives shipments from 3 different parts vendors. There's been a defect with some of the electrical wiring in the rec vehicles manufactured at the plant. The plant manager wonders if all the vendors might be contributing equally to the defect issue. The plant manager reviews a sample of quality assurance inspections from the last 6 months. The data are shown in the table below. Test an appropriate hypothesis to determine if the plant manager is correct. So the plant manager is wondering if all vendors are contributing equally. In other words, if the percentage of defects is the same across all the vendors. So this would definitely be 3 separate samples here, right? One from each of the vendors, looking at how many parts were rejected and how much were perfect and how much were not perfect but acceptable. So it looks like I've got in each vendor, I've got parts that are perfect, parts that aren't great, but we can still use them, and parts that we had to reject. And we want to know if these percentages are the same across the 3 vendors. So this one's definitely a chi-squared test of homogeneity, because we're trying to show whether the distribution of quality level is homogeneous across the 3 vendors, the 3 populations. All right, so in that case, the null hypothesis and alternate hypothesis have this form. We would say something like the percentages of each quality part is homogeneous across vendors. So the same percentage of rejected parts, the same percentage of perfect parts homogeneously across all the vendors. The other one would be the percentage of each quality part is different from vendor to vendor or across the vendors. Right, so it depends on what vendor we're talking about here, right? But I don't want to use language like dependence, right? Because that would make this a chi-squared test for homogeneity. I want to say these percentages stay the same across all the vendors. Okay, we've got to check conditions. Oh, I forgot to check conditions on the last part. Before we clear the calculator, let's go back. I forgot to fill this in. Did we meet the expected counts? So when we're done with the analysis, we have to go back and look at matrix B and just make sure that none of the counts are below 5. And sure enough, they're all fine. What I like to do is just show people that I've done it is I write down the lowest count. I put yes, and then down here I say the lowest is 55.8, just to kind of show people that I checked that. Forgot to do that. We're going to do that here. So we've got 3. We've got count data. Do we have count data? Yep. Do we have an SRS? It says reviews a sample. So we did a sample. So I'm presuming that this is a representative sample. And then for expected counts, at least 5, we'll check that at the end. Okay, we're going to run a chi-squared test in the calculator. I should probably call it a test of homogeneity. Just somewhere on the page you have to indicate, even though it's really called a chi-squared test, you have to write the word homogeneity somewhere. Identify it as a chi-squared test of homogeneity. And that means we're going to go to our matrix, edit matrix A, make it, in this case, a 3 by 3 matrix, right? And then enter these data: 53, 48, 70, 93, 71, 88, 22, 31, 22. And then we can go ahead and run a chi-squared test on that matrix. Okay, let's write down what's here. Chi-squared is 7.4. That's the test statistic. The p-value is 0.116. Degrees of freedom were 4. 3 minus 1 times 3 minus 1. 2 times 2 is 4. And then while we're at it, let's check the expected counts to make sure that they were also okay. If I look at matrix B, let's see, there's a 25.3 there. There's a 22.5, right? But they're all well above 5. 22.5. I'm going to put the lowest count was 22.5. So that's good. That's met too. It means we can use this value. And we would say with alpha is 0.05. P-value is 0.114 is high. So we fail to reject the null. And because we failed to reject, we do not have sufficient statistical evidence to conclude that the percentages of quality are different from vendor to vendor. Right, so we're basically saying that the percentages are about the same of rejected and perfect parts from all the vendors, but we don't want to say it as accepting the null. We have to say we don't have evidence that there's a difference. All right, so that's how we would do that. All right, so that'll wrap up the video. I think we've seen everything that we need at this point to do any of the problems in the Chapter 26 required practice packet.